and welcome to the University of Toronto's Self-Driving Car Specialization. My name is Stephen.
And my name is Jonathan, and we'll be your instructors throughout this specialization.
The self-driving car is the sleeping giant which can change everything. Road safety, mobility for everyone, while dramatically reducing the costs of driving. This specialization will teach you what you need to know to kickstart a career in the autonomous driving industry. Whether you're coming from academia or industry, these courses will provide you with the foundational knowledge and practical skills you need to help build a new future with self-driving cars. Throughout the courses, we'll show you real-world data and scenarios from our research and from our own self-driving car, or what we call the Autonomous. After decades of applied and award-winning research, we at the University of Toronto are excited to show you the nuts and bolts of autonomous driving. There are a total of 4 courses in this specialization. In the first course, I'll introduce you to the self-driving car software and hardware architectures. By the end of this course, you'll be able to design a basic hardware system for a self-driving car, identify the main components of the autonomous driving software stack, and create a safety assessment strategy for a self-driving car program. You'll then learn to develop the complete model of a vehicle's motion, define a PI controller for longitudinal control, define a path-following controller for lateral vehicle control, and test out your control designs in the carless simulator.
In the second course of the specialization, I'll teach you about state estimation, sensing, and localization for autonomous vehicles. By the end of this course, you'll understand the key methods for parameter and state estimation, develop and use models for typical vehicle localization sensors, apply extended and unscented Kalman filters to a vehicle state estimation problem, and register point clouds created from LiDAR scans to a 3D map of a static environment.
In the third course, I'll teach you about visual perception for self-driving cars. After completing this course, you'll be able to project 3D points onto the camera image plane, calibrate the pinhole camera model, apply feature detection, description, and matching algorithms for localization and mapping, develop and train neural networks for both object detection and semantic segmentation. You'll apply these methods to vehicle tracking and drivable surface estimation. And in the fourth and final course, I'll teach you about motion planning for self-driving cars. By the end of this course, you'll be able to devise a trajectory rollout motion planning method, calculate the time to collision with static and constant velocity objects, plan routes over complex road networks, define high-level vehicle behaviors and transitions for vehicles navigating through intersections around parked cars and merging, and develop kinematically feasible paths through an environment with static obstacles, compute velocity profiles that satisfy speed, curvature, and moving object motion planning constraints, plan behaviors and execute maneuvers to navigate safely through the world, and gain valuable experience in debugging and testing self-driving algorithms in the carless simulator. So by the end of the specialization, you will have a detailed understanding of the architecture and components of the autonomous driving software stack, and will program your own self-driving car. Since we're teaching you how to program your own self-driving car, the courses in this specialization have several prerequisites. First, you should be proficient in linear algebra and be familiar with matrices, vectors, matrix multiplication, rank, eigenvalues in vectors, and inverses. This background will help you with control, state estimation, perception, and planning algorithms throughout the courses.
You should also be comfortable with statistics, and in particular, working with Gaussian probability distributions. This knowledge will be important for state estimation and for perception when we're estimating vehicle speed and heading from GPS and inertial measurements, for example. You should also be comfortable with basic calculus and physics, such as forces, moments, inertia, and Newton's laws. It's certainly helpful to know how to drive a car, but since the cars will be self-driving, it's not a hard requirement for this specialization. If you don't have these necessary prerequisites, there are excellent robotics, AI, deep learning, and other courses that you can take on Coursera to prepare you for this specialization.
Autonomous driving is a constantly evolving and changing field, so keeping up not only with self-driving knowledge, but also robotics, AI, and deep learning will help you keep your technical skills sharp. There's a long way to go, and we need pioneers to help us get there.
So are you ready for the ride?
Hello everyone, welcome to this video in which we roll through the many major milestones in the rapidly evolving story of self-driving cars. A driverless future seems just around the corner, but it's been a long, arduous journey to arrive at this point.
The dream of self-driving cars is almost as old as the automobile. As early as 1925, Francis Houdina demonstrated a remote control car called the American Wonder, which drove through the streets of Manhattan, frightening passerbys with an empty driver's seat. Houdina, a local mechanic, is not to be confused with Harry Houdini, the famous escape artist, who was rather upset and started an altercation when people accidentally attributed the marvel to him. The self-driving car dream was alive and well in 1956, as GM released a promotional video claiming self-driving cars would arrive by 1976. In The Key to the Future, GM saw humans handing over control on the highway, enjoying a stress-free drive, and the passengers even interacting with the car through voice-activated control features. A little optimistic, but in terms of timing, it's amazing how many of this video's predictions are now becoming available in the market.
And this dream's inspiration comes straight from the reality of driving in busy traffic. There is no doubt that one of the most dangerous things we do on a regular basis is driving our car. In fact, more than 94% of all driving accidents today are caused by some kind of human error. What if we could minimize or completely eliminate driving deaths by taking human error out of the picture through automation?
There are also many other profound benefits that could arise from a driverless future. Instead of focusing on lanes, turns, and traffic, you could reply to work emails, eat, or relax and make the morning so much more productive. And we can extend the mobility that driving provides to the entire human population, not just those able to perform the driving task.
Let's go back to the beginning of the self-driving car story and take a look at the milestones that have defined this industry, at the breakthroughs that make it all seem possible, and at the setbacks that remind us how ambitious this vision of ubiquitous autonomy really is. Our journey starts out with some early advances in Europe in the 1980s. Pioneers have been working on self-driving technology for over 40 years, with early vehicles mostly partially autonomous and operating at low speeds. In 1986, Ernst Dickmanns and his team from the University of Munich pioneered a robotic van that could drive fully autonomously without traffic, and in 1987 it drove its speeds up to 60 kilometers per hour.
In the early 1990s, his team contributed significantly to the Eureka Prometheus project and developed an autonomous Daimler-Benz using saccadic computer vision, that is, focusing on points of interest in the environment. They had over 50 transputers, the latest microprocessors of the day, and the same probabilistic approaches used throughout robotics on board to fuse sensor input and react to road situations in real time. Ultimately, the Daimler-Benz drove 1,600 kilometers in traffic from Munich to Copenhagen with a mean distance between human intervention of 9 kilometers. At
the same time in the US, Carnegie Mellon University's Nav Lab was busy building a steady series of prototypes with ever-improving capabilities. In 1986, their first autonomous vehicle, Nav Lab 1, managed 30 kilometers per hour on the road using multiple Sun workstations. Then, in 1990, Nav Lab 2, a modified Humvee which could perform autonomously both off and on road, reached autonomous speeds of 110 kilometers per hour on the road. This pushed the team to attempt something much more ambitious, and in 1996, they completed their No Hands Across America tour, a 4,800 kilometer route across the continent with an impressive 98.2% autonomous driving.
Soon after, the UC Berkeley PATH project rose to prominence with successful demonstrations of autonomous platoons of vehicles operating on dedicated HOV lanes on the I-5. In 1992, 4 vehicles drove in convoy at highway speeds, relying on magnetic markers on the roadway for precise relative positioning, and demonstrated that using this kind of convoying saves on fuel costs and reduces wind drag. Successful tests continued, and in 1997, large-scale demonstrations with 8 to 10 vehicles were completed. The project also firmly established the use of radar systems and vehicle-to-vehicle communications in the AV industry, leading to advances such as adaptive cruise control and emergency braking.
Then, in 2002, DARPA, the Defense Advanced Research Projects Agency, announced the first of its grand challenges that would forever change the world's perception about what autonomous robots can do. The first event was held in 2004, and DARPA offered the winners a $1 million prize if they could build an autonomous vehicle that was able to navigate 142 miles through the Mojave Desert. Although the first event saw only a few teams get off the start line, and Carnegie Mellon's red team taking first place having driven only 7 miles, it was clear that the task of driving 140 miles through the desert without any human aid was indeed possible. In the second DARPA Grand Challenge, the next year, 5 of the 23 teams smashed expectations and successfully completed the track without any human interventions at all. Stanford's vehicle Stanley won the challenge, followed by Carnegie Mellon's Sandstorm. The era of driverless cars had arrived.
Later, the 2007 installment, called the DARPA Urban Challenge, invited universities to show off their autonomous vehicles on busy roads with professional stunt drivers. This time, after a harrowing 30-minute delay when the Jumbotron screen blocked their vehicle from receiving GPS signals, the Carnegie Mellon team came out on top, with Stanford's junior vehicle coming in second. The 3 grand challenges were truly a watershed moment in the development of self-driving cars, changing the way the public and, more importantly, the tech and automotive industries thought about the feasibility of full vehicle autonomy.
It was now clear that a massive new market was opening up, and the race was on. Google immediately brought the team leads from both Carnegie Mellon and Stanford, Chris Urmson and Mike Montemerlo, to push their designs onto public roads. By 2010, Google's car had logged over 140,000 miles in California, and later wrote in a blog post how they were confident on cutting the number of traffic deaths by half. Their pursuit of this ambitious goal continues to this day, with the team having logged over 10 million miles as of October 2018.
Around the same time as the first autonomous testing in the US, 2 orange vans from the VisLab completed the International Autonomous Challenge, driving an entire route from the University of Parma in Italy to Shanghai, China, which was about 15,000 kilometers, with minimal driver intervention.
A year later, Volvo demonstrated their road train concept, in which one vehicle could control several other vehicles behind it, thereby reducing road congestion and improving driver comfort. Car drivers could choose a lead truck to follow, but the close following led to frequent vehicle damage and low visibility in rainy conditions.
As the pace of development accelerated, more and more companies were pushing for a legal framework for on-road testing. In 2012, the Nevada Department of Motor Vehicles issued Google the first ever autonomous vehicle testing license, which meant they could now test autonomously on public roads. California soon followed suit, with a mandated requirement to publish a variety of statistics on the tests performed and the rates of human intervention.
In 2013, 125 years after the first Bertha-Benz car was demonstrated for public use, Mercedes-Benz demonstrated their self-driving capabilities by covering the same 106-kilometer route autonomously. With multiple players demonstrating viable on-road demos, public interest in autonomous driving has taken off. The Consumer Electronics Show in Nevada became the annual showcase for the greatest self-driving tech and the wildest vehicle redesigns.
About a year later, Google demoed their Firefly car, a vehicle designed from the ground up to be autonomous at speeds up to 40 kilometers per hour. With no steering wheel or pedals, passengers can instead sit back and relax, and only press one stop button if they feel uncomfortable. By doing so, Google showed us what the AV future could look like.
And Tesla wasn't far behind, and around the end of 2015, they introduced their suite of autonomous features into the software called Autopilot. By 2016, they had demonstrated how Autopilot could self-park and could be summoned by a button. This represented the largest deployment of partially autonomous features at the time, and saw Tesla quickly racking up millions of kilometers driven with their Autopilot.
Inevitably, however, as the number of autonomous miles driven expanded, the first fatal accident involving a Tesla Model S happened in Florida in 2016. This was caused by a simultaneous failure of both camera and radar sensors to correctly identify a left-turning transport truck and an inattentive driver used to a car that takes care of itself. This setback demonstrated the dangers of reliance on human monitoring of self-driving systems.
Despite this setback, progress continued unabated. This was also the time the notion of autonomous taxi fleets were becoming popular, with startups like Zoox and Nutonomy leading the way. In fact, Nutonomy taxis first became operational in Singapore in 2016.
And finally, we arrive at 2018 and the infamous Uber crash that claimed a pedestrian's life in Arizona. This incident sent shockwaves through the autonomous vehicle testing community, with Uber stopping testing until the details could be fully understood through an independent investigation by the National Highway Traffic Safety Administration. We'll discuss this worrying case in more detail in the first course, as an example of the challenges that remain in self-driving systems.
So the story of the development of autonomous vehicles is a story of enormous successes, as well as setbacks that seem to be happening more often recently. So what is it that's driving the increase in self-driving accidents during testing? First, the number of miles being driven by self-driving cars in hard conditions is exploding, so the number of accidents are bound to go up.
In fact, Waymo recently announced that as of fall 2018, they have completed over 10 million miles of autonomous driving. The time between human interventions continues to grow, with the most advanced systems traveling thousands of kilometers without any intervention at all. Human-level performance appears to be just around the corner, but the industry needs more support than ever to meet and exceed this ambitious goal.
Many new and established companies are pushing to bring truly driverless cars to market as early as 2020. The first large-scale deployments will be in fleets, where companies own the vehicles and provide revolutionary new services like robotaxis and driverless delivery. The technology is still quite expensive, but prices will fall quickly as economies of scale take over. So much still needs to be done to bring about the transformational changes we expect driverless cars to bring to our society. The industry will continue to need outstanding engineers to produce innovative solutions for driving.
So I guess the real question is, are you ready to help shape the future of personal mobility? I'm Kelly, and I am an assistant professor at the Institute for Aerospace Studies at the University of Toronto, Canada. As a child, I used to love to go every month to the magazine store, and I would always read Popular Mechanics or Popular Science. They had all these interesting articles about things from space travel to new vehicles to new computing designs, just really interesting stuff. And so that's ultimately what prompted me to start looking at science and technology as a possible career choice. One of the things that happened when I was quite young was the first space shuttle disaster, the Challenger disaster. I can still remember that actually, and thinking just, my goodness, that something must have gone wrong, and just how dire the consequences were, this tremendous explosion. At the time, I just remember sitting stunned thinking, technology sort of always worked. That was my opinion. Well, technology always works. It doesn't fail. Cars don't just explode. And then seeing this on television really brought it home that engineering really does matter. Solid engineering is critically important in these life-threatening or potentially life-changing situations. Self-driving cars are in many ways very similar, right? We have a responsibility as engineers to design these systems to be as safe and reliable as possible as we can. It's one of the things that's the most exciting technology revolutions that's really coming in the near term. New ideas, new technologies, new designs are coming down the pipe every single day. I often just sit down at my desk and my eyes sort of pop when I see the number of innovative new ideas and techniques that people are coming out with. It's also excitement from a point of view of actually changing the technology landscape and doing something that will potentially benefit a lot.
I'm Diana Burgess, and I currently work at Zoox on the firmware team as a firmware engineer. A brief background about me: I have a bachelor's of mechatronics engineering from the University of Waterloo, where I've gone through a lot of internships and worked at a lot of different jobs. Most recently, I've worked at Before Zoox, I worked at Peloton Technology, which does semi-autonomous trucks. I actually got that job because I had done an internship with Bendix, which does brakes for trucks. So I got into autonomous through a bit of a roundabout way, going through the trucking industry before going to full autonomy with Zoox. I got interested in robotics from an early age in high school. So I'd always been interested in engineering in general and had thought I would do mechanical engineering in university. But in high school, I took some computer courses and learned I liked programming as well. So I thought mechatronics was a good idea. I'd also joined a robotics team, a FIRST robotics team. On that, you get to build a complex robot to compete in a game that changes every year. So you have to build a whole new robot to compete in the next year's game. And each game has both an autonomous component and a driver-operator component, so you have a lot more complex things to do for that. So I got really interested in robotics through those experiences, and it just sort of solidified through university. I currently work on the firmware team. A lot of my job entails working on one of the main motion control units, which in the vehicle helps to work with each other part of the vehicle to control it to.
Welcome to the third and final video of this week. In this video, we will be discussing decision-making in the self-driving car system. Recall that in the last video, we discussed perception, which forms the first step in performing a driving task. The other, how do I follow my lane on this curved road? And what steering input should I apply? Should I accelerate or brake, and if so, by how much? Let's discuss a very simple example of a driving task and try to think about what kind of decisions are involved.
Note that throughout this specialization, we will assume right-handed driving for all scenarios.
Suppose you're approaching an intersection on your way home. The long-term planning stage requires you to turn left at this intersection. Now let's look at the intermediate and short-term decisions that need to be made. First, let's assume that the intersection is controlled. That is, it has traffic lights. Since you are turning left, you have to identify if you need to make a lane change into a left turning lane. Then, as you're approaching this intersection, you choose to slow down, and to do so smoothly so that the passengers don't experience discomfort. Nobody likes a jerky driver, after all. You then come to a stop just before the stop line, before a pedestrian crossing. These decisions on lane changes and stopping locations are all short-term planning decisions. But wait, you also need to think and respond to situations that arise along the way. We still need object and event detection and response. What if a vehicle pulls into the turn lane in front of you? You would want to stop earlier to make room for the other vehicle. What if the stop lines weren't marked? You would have to approximately judge where the implied stop line is and stop before the pedestrian crossing. And what if there were other vehicles behind you or even stalled in the intersection? How does the decision to execute a left turn change based on the many possible scenarios that can rapidly arise in normal driving? All of these decisions fall into the immediate decision category and require safe reactions from the planning system. The end result is an exploding list of possible decisions to evaluate on different timescales, even for a simple left turn scenario. This amounts to talking about different cases for the same intersection crossing, or scenarios. In each scenario, we need a consistent set of choices to be evaluated in real time and updated as new information about the scene becomes available. Furthermore, because decisions to change lanes affect where to drive and which cars to regulate our position relative to, even a seemingly simple driving scenario requires 3 or 4 levels of decisions and must then still be executed with careful vehicle control. This example is really only scratching the surface of the constant stream of decisions needed for motion planning. The bottom line is, driving is complicated. Let's go ahead and discuss a possible structure to represent these decisions in software. One method to address the challenge of multi-level decision-making is reactive planning. In reactive planning, we define sets of rules that take into account the current state of the ego vehicle and other objects in the environment and produce immediate actions. So these are rules that only consider the current state and not future predictions. Some examples of such rules would be, if there is a pedestrian on the road, stop. Or, if the speed limit changes, adjust your speed to match it. In both of these rules, we just observe what is happening right now and make our decision based on immediately available information. But there are other kinds of planning as well. In predictive planning, we make predictions on how other agents in the environment, like vehicles and pedestrians, will move over time. We use this current state and prediction information to define all of our decisions. Some examples of rules in predictive planning would be, that car has stopped for the last 10 seconds. It's probably going to stay stopped for the next few seconds. So perhaps there is a way that I can move past it safely. Or, a pedestrian is jaywalking. They will enter our lane by the time I get close to them. Let me slow down and give them a chance to cross the road ahead of me. As you can see, this is a more natural way to think and relates closely to how humans operate vehicles. We predict where other objects on the road will be in the future before we make our decisions. This type of planning, however, relies on accurate predictions of the actions of the other actors in the environment. We will discuss all aspects of planning in the further detail in Course 4 on Planning for Self-Driving Cars, where we will show you the methods to solve long-term, short-term, and immediate-term planning problems. All right, let's summarize this video. We discussed the planning problem and the different types of planning based on the window of time over which we have to act. These types are long-term, short-term, and immediate planning. Then we discussed a simple intersection scenario where we had to make a left turn. We concluded that driving is a really hard problem since we have so many variables and possibilities that result. Then we discussed two different planning approaches, reactive planning and predictive planning. And this is just the tip of the iceberg. There's clearly so much more we need to think about before making a decision during the driving task. Once again, we'll go through all of these ideas in much greater detail in Course 4. That brings us to the end of the first week of Course 1 in our self-driving car specialization. Let's quickly recap what we learned this week. In this module, we explored the basic autonomous driving terminology that's useful for later weeks of the specialization. We then discussed the levels of automation and came up with a taxonomy to characterize self-driving capabilities. Then we defined the driving task and the major components of driving: perception, planning, and execution. We then listed the elements and agents in the environment we need to identify and track for perception, and we also discussed why perception is so hard. Then we discussed planning with its different horizons and looked at some decision-making approaches. In the next module, we will define the main components of self-driving cars, including both the hardware and software elements that make up a complete system.